Hello, this talk is about sound field reproduction with weighted mode matching and infinite dimensional harmonic analysis. I'm Shoichi Koyama from the University of Tokyo. Sound field reproduction is aimed at synthesizing a desired sound field inside the target region with multiple loudspeakers. We here focus on numerical sound field reproduction methods rather than analytical methods. The numerical methods are based on the minimization of error between synthesized and desired sound fields. One of the benefits of the numerical methods is the flexibility of loudspeaker array geometry. Furthermore, they can be applied in a reverberant environment by measuring impulse responses of the secondary loudspeakers in advance. We compare two numerical sound field reproduction methods in a practical environment: pressure matching, PM, and weighted mode matching, WMM. We also apply infinite dimensional harmonic analysis for estimating expansion coefficients of spherical wave functions in WMM. We first formulate the sound field reproduction problem. The goal is to synthesize the desired sound field U-des inside the target region omega with L secondary sources, loudspeakers. The optimization problem is formulated as this equation. Here, G is the transfer function vector from the secondary sources to the position R, and D is the driving signal vector. So this term means the synthesized sound field. And the cost function is represented as the regional integration of the square error between synthesized and desired pressure fields. This minimization problem is actually difficult to solve because the existence of the regional integration. Pressure matching, PM, is a widely used sound field reproduction method in practice. First, the target region omega is discretized into n control points, as in this figure. Then, the previous optimization problem is approximated as a simple linear least squares problem. Here, G is the transfer function matrix between the secondary sources and control points. Second term is the desired pressure vector. We also added a regularization term to prevent an excessively large value of D. The closed form solution of this least squares problem is simply obtained as this equation. The pressure matching is widely used in practice because of its simple implementation. However, this method is based on the discretization of regional integration. As a result, the target region omega essentially should be finely discretized to achieve high reproduction accuracy. Weighted mode matching is an extension of the well-known mode matching method, which is recently proposed by the authors. In a similar way to the mode matching, this method is based on spherical wave function expansion of a sound field, which is series expansion by using spherical harmonic function multiplied by spherical Bessel function. The desired sound field U-des and the transfer function vector G are approximated by the spherical wave function expansion up to over order NTR. Here, phi bar is the finite dimensional vector of basis functions, and B and C are the vector and matrix of the expansion coefficients, respectively. The previous objective function, including regional integration, can be approximated by the series expansion as this equation. Here, C and B are expansion coefficients, and W is the weighting matrix defined as this equation. Then the optimization problem of WMM is described as this equation, which is the minimization problem of this cost function with the regularization term. This problem also has a closed form solution shown below. Here, the weighting factor for each expansion coefficient is determined by this matrix W, which is the regional integration of spherical wave functions. Next, we introduced the infinite dimensional harmonic analysis for estimating the expansion coefficients B and C using a microphone array of arbitrary geometry. Estimation of B is necessary to reproduce a captured sound field. Estimation of C is necessary to use measured transfer function for canceling reverberation in reproduction. First, the microphone signal S and expansion coefficients of the sound field around the position R, which is denoted by alpha R, are related by this matrix. Here, lowercase c is the expansion coefficients of the directivity pattern of each microphone. T is the translation operator that relates the expansion coefficients at two positions. As a result, the expansion coefficient alpha is estimated as this equation. It seems a simple least squares solution, but the important point is each element of this metric psi is analytically calculated as in this equation. We use some properties of the translation operator to obtain this. And this estimator has some important properties. One is that the truncation of the expansion order is unnecessary because the metric psi is obtained by using infinite dimensional expansion. Moreover, this psi is independent of the expansion center R. Please refer to this paper for the details of this estimation method. We evaluated the introduced sound field reproduction methods using real data measured by practical array system. We used an impulse response dataset we recently released, which is called Mesh RIR dataset. The main feature of this dataset is that the impulse responses at finely discretized grid points are available, so it is suitable for evaluating sound field recording and reproduction methods. This is a wave motion visualized by this dataset, and impulse responses at each measurement point was obtained by using this Cartesian robot equipped with an omnidirectional microphone. In this experiment, a single plane wave field was synthesized. The target region was 2D square region of 1 meter by 1 meter. The number of loudspeakers was 32, and the arrangement is shown in this figure. The microphones were uniformly distributed over the target region omega, which was used as the control points in the pressure matching and for estimating expansion coefficients of the transfer functions in the weighted mode matching. And the number of evaluation points was 441. The source signal was a low-pass filtered pulse signal whose cutoff frequency was 700 Hz. We compared the reproduction accuracy of PM and WMM. The evaluation measure is SDR, defined like this. So a higher value of SDR means high accuracy. And this is a reproduced pressure distribution in the case that 36 microphones were used. These crosses indicate the position of the microphones. And these are the pressure field of true, WMM, and PM. And these are the time averaged error distribution. SDR was 4.64 dB for WMM and 4.67 dB for PM. So the difference between these two methods was small in this case. But when the number of microphones was reduced to 16, the reproduction accuracy of PM deteriorated. SDR was 4.65 dB for WMM and 3.85 dB for PM. And this is a plot of the relationship between the number of microphones and SDR. WMM outperformed PM when a small number of microphones are used. So we conclude this talk. We have shown experimental evaluation of two sound field reproduction methods, pressure matching and weighted mode matching. WMM is based on the circular wave function expansion. And we also combined the infinite dimensional harmonic analysis with WMM. The experimental result indicated that WMM outperforms PM when a small number of microphones are used. So, thank you for your attention.